Va bene. Allora, buongiorno, io come anche as the preceding speaker, I will go standing up. I never presented a paper sitting down, so I apologize if I make you nervous about that. So, best wishes from the city where they say that Homer composed the Iliad and the Odyssey. I'm working in Smyrna. There is a community of Italians over there. So, thank you for the invitation, especially for Adele that has done the impossible things with a person she hardly knew. So, thank you so much for that. Really wonderful. This is a very, it's a field in explosive expansion. So the presentation to be done in 15 minutes will have slides that will look subliminal to you, really. It's going to be pretty quickly presented. I appreciate your interest, of course, and if there are any questions, just speak to me afterwards. So the points I want to make in the presentation is that if we look at, this is the Aegean Sea with waves spraying out there. You see droplets. I live in the city of Clazomene, where Anaxagoras lived until he brought philosophy to Athens, the tradition is. And the question is, as you know, philosophically, what holds these things together? We are very proud of the atomistic system that was introduced by Epicurus. But the question is, it's beautiful to say that matter is composed of bits and pieces that come together and then they come apart and things live and die like that. But to do that, you need to have atomic forces. Of course, remember that the word atomic and the word force would not have been known at the time, but there has to be some kind of way for these things to hook together. The story I want to tell you today, in super brief fashion, is the story of how these forces, besides being of philosophical interest and physical interest, are now becoming of industrial interest, although this appears extremely unlikely and just a few years ago would have been considered crazy to imagine. In reality, they are becoming the centerpiece of development in nanotechnology. We have this statement by Epicurus in which, the statement of existence of atoms that is very famous for those who are in love with the atomistic system. But you need to have this idea of entanglement, and not in the sense of optical physics today, but in the sense of atoms cohering together. That needs to be specified. So I'm just presenting these obvious quotations to include the fact that they knew that there was a problem, that these things had to hold on together. Now, we are also, at least I am an educator, and I find myself in the classroom telling students that neutral objects do not attract. That's what we teach children, right? That negative and positive attract, like charges repel, negatives do nothing to each other, which is of course a lie. If that were true, this couldn't be possible. Okay? So, great minds devoted themselves to understanding how this was possible. And we have Galileo here making an obvious blunder, in which he says that the forces that hold droplets of water together are external forces, not internal forces. And Newton, in the preface to the Principia, which for some reason that I don't understand, Hawking did not include in his edition of the Principia, he declares that he doesn't know what these forces are, interatomic forces. They were aware of it. Newton in the optics talks about forces between glass, for instance, different lenses holding together. There is a beautiful experiment that experts in Casimir forces like to show even at research conferences, in which none other than Boyle is showing here discs of marble that are finely polished under vacuum, and he lowers one disc to the disc that is sitting on the ground. They make contact and he picks it up. Completely neutral objects. So don't tell the children that neutral objects do not attract, obviously. Now the problem is that Boyle was doing this having a very different hope. He was hoping to show that by pumping the air out, these discs would drop off of each other. That was a huge debate with Hobbes that I'm sure you're familiar with. So for him, this was a tragedy. And in order to make the point that these things, that the disc at the bottom was coming off when the air would be pumped out, he actually attached something to it. And he states to make it easier for the bottom disc to fall. Well, the bottom disc wouldn't fall because there was actually a strong force of attraction, of cohesion between these two discs. He concluded characteristically that the experiment was wrong and he had failed. In reality, he has simply experimented with what we call today van der Waals forces. So we have a beautiful statement here by Santayana in which he discusses the importance of atomism in the history of science. He describes it as none other that, that the most important idea that humanity has ever had. But in order to work, we need to have these forces attaching things together, otherwise it makes no sense. And I would like to say that there was a period that the old, of course I live in a Muslim majority country, so we also pay a little bit of attention to science done east of Italy. And Al-Kazini, in the book of the Balance of Wisdom, talks about the fact that fluid flowing through a narrow channel has difficulty to come out on the other side, which makes this water balance very difficult to use when the fluid has to go through a small channel. We call this capillarity, which is connected to van der Waals forces. Okay, so Kanikov, that translated the book of the Balance of Wisdom in the 1800s, concludes that capillarity action was known to the Arabs, although it's unclear. Remember that for those of you who aren't familiar with this field, that what the Arabs are is not clear here, because Al-Kazini was actually a Greek slave in Merv in Persia, writing in Arabic. So it's not so easy to understand what that means, really. All right, so the point I want to make today, now that I've introduced the subject, is this, that, this is the New York Times in 1998, I think it was. This is Cabasso at Bell Labs, that is Lucent today, making an experiment in which they basically take a small sphere, they take it very close to a surface that can do this, and this platform, this little surface, is actuated by the force exerted by the sphere. So basically, he can actuate a neutral nanostructure by using van der Waals forces. Okay. So the experiment is an elegant demonstration of something that is basically a Cavendish balance on the nanoscale. But what's interesting to me is the title of the New York Times. A tiny force of nature is stronger than thought. What does this mean? This is very good. Thought by whom? So bottom line is, there is in the history of physics, there are two schools. Interatomic forces are tremendously strong. We got to be careful. They're going to destroy the device. But then there's the other school. Interatomic forces are exotic and weak. It's going to be difficult to detect them. And these two groups march together into conferences at the same time. So this poor journalist, Kenneth Chang, that is actually famous for science writing, had to reconcile these two, because now you got here this force that is exotic and weak, very difficult to detect, remember? But now they're actuating nano devices with it, So what's happening? So you say, well, why does anybody care? Well, because you can always find neutral objects, even on the nanoscale, nanotube and nanotube, easy to find. But if you want to charge them, you need to have wires. So there is a limit intrinsically to the architecture that you can have. If you can make stuff like this, you can make the equivalent to transistors on the nanoscale, which you cannot do with electronics today. So this is a huge, major breakthrough in technology made possible by van der Waals forces. So at the maximum speed that I can go, I want to tell you that these forces depend on the optical properties of materials. It depends on roughness, it depends on whether the object is reflecting or not, it depends on whether it's a conductor or not, a dielectric, it depends on temperature. So we all know that they depend on things, okay? But what's interesting is that, of course, if two atoms attract each other, then two surfaces should attract each other. There is, if you read in the literature, the mystery of the Casimir effect. So Milonni has written about this. Well, the fact that two atoms can attract each other is a mystery. That really wasn't understood until more or less London, for the first time correctly, explained it quantum mechanically. Okay, this cannot be done in classical physics unless you assume the existence of a stochastic electromagnetic field in the room. That is very controversial. So historically, the first time that this interaction was explained correctly as a force, as a potential that is inverse to the 6th power of the distance, was by London. Now you've got pairs of these, you add them up, you get forces between surfaces, so it's not a surprise. But you're going to find today the mystery of the existence of these forces. So the paper by London is a breakthrough and simple to understand. It's spectacularly simple. I think that an undergraduate student in the second year could understand the paper by London. Now, Casimir, there is a very famous name in this, comes in with a different problem, an industrial problem. You know, usually you would find Casimir cited as a theoretical physicist, but he was actually an industrial man. He became the vice president of Philips. And the problem he had was this: they were having and these colloidal particles were attracting each other. So the van der Waals forces are critical to colloid experts. But when the particles were far away, this force appeared to decay much stronger than expected. This was the mystery of the van der Waals forces decaying too fast. So Verwey and Overbeek suggested that perhaps it had to do with retardation, meaning that the speed at which light travels from an atom to another makes a difference. Imagine, you are at the micrometer scale or less, and the distance at which speed of light, the time that it takes for light to travel from an atom to the next makes a difference to the intensity of the force. It was a very bold suggestion, you know, in the early 1940s. So Casimir and Polder took that on, and they discovered that it is true. In reality, that retardation has an effect, and it changes the power potential from 1 over to the 6th to 1 over to the 7th. That would be the Casimir force. So accelerating even further, I want to tell you that the man who unified all this was Lifshitz. The students here will remember Landau and Lifshitz. We used to joke that in the Landau and Lifshitz books, there is not one word by Landau and not one idea by Lifshitz, right? That's what he used to say. It's not true. Lifshitz actually put in some of the most intense mathematics in that volume, in particular the one on statistical mechanics, in which he formulates the theory in 1955 of unification of van der Waals forces and Casimir forces. This is the first time in which everything comes together. The London force, the van der Waals force, the Casimir force, everything is in it. Solid objects, particles, everything is in that same theory. A masterpiece of theoretical physics. So here, if you calculate the force between two planes at the retardation range, you see that the force goes down as 1 over d to the 4th for two plates I'm talking about now. And instead, if you are very close, it's unretarded, and you've got that situation there. So I want to show you, if I can just spoil your hearing for a minute. This is two plates, and instead of using the electromagnetic field, we're going to use an acoustic field, which is going to bother you now. Sorry about that. You see these two plates are moving. Okay? So this is basically a simulation of what the electromagnetic field does, only done with an acoustic field that is imposed by speakers from the outside. So I have an undergraduate student who has done this. We didn't discover this. It was done by La Raza in 1998. Okay, so now I'm going to stop this horror of a noise. So obviously time is not going to help me on, but I want to connect it to this very super famous quotation from Feynman, 1959, when he says, hey, be careful. Nanotechnology is going to be limited. He didn't use that word, obviously, because van der Waals forces here are going to make it impossible for you to operate. You're going to touch something, it's going to stick to you. So here we go. Now we are transitioning from this force is, you see what Casimir said was, although the effect is small, an experimental confirmation seems not unfeasible, all the way, now you are here with Feynman, be careful, this is going to stop you from doing anything you want to do. Okay. And so a few years later, McLeay, in a very famous paper, starts to say, wow, this actually is going to, if you have an oscillator, the behavior of the oscillator will completely change depending on the presence of these forces. So, and at the same time, Robert Forward, who actually was an expert in gravitational wave research, a student of Weber, came up with the idea that you store energy in the van der Waals field. So you see the transition from it's weak and we don't understand it, it's a mystery, to it's a danger, to we want to use this thing. Because we got now the strongest force of nature, bar none, between uncharged objects, is transitioning from nuisance to opportunity. So the interesting story here is this group of German scientists, Hunklinger, Arnold, led by Dransfeld in the 1970s, they had the idea to say, hey, if this force depends on the optical properties of the material, if we change the optical properties of the material, we can change the force. And that was the beginning of my own contribution to the field, that if we can do that, then we can do a thermodynamical engine cycle, and we can make nano engines based on van der Waals forces. So, of course, time is running out, so I'm going to just show you here Casimir, who, in my opinion, a shame to history, didn't get the Nobel Prize for his discovery of the Casimir effect, but he had this idea of the interaction between academia and industry. He called it the spiral, and I wanted to show that to you. And a view of the experiment, which is kind of clunky by our standards, in which they demonstrated the dependence of van der Waals forces on illumination. So they were illuminating two semiconducting surfaces, and the force between that semiconducting force and another surface was changing in time. So I want to skip forward and conclude with the only thing I can show you. This is me with Arno Penzias, that you may know, the discoverer of 3-degree background radiation, winner Nobel Prize in 1978. But when did I meet him? I met him in Silicon Valley. He's now an advisor to venture capital firms, where he was listening to how you can transform technology in, this exotic field into actual technology. A scary man. I mean, he was pounding on the table for 3 hours, telling me that the physics was wrong, and speaking half in Yiddish, half in English. And eventually, I convinced him, though. So I want to tell you, this is happening. In fact, this is going to scare you even more, maybe, but these are good people with PhDs from Western universities, friends of mine that have been very interested in pursuing this. This is Saudi Arabia. I spent 4 years there. And I just want to show you the end of the story, because I know that they want me to finish here. So remember, this is a weak force. It's exotic, hard to detect. And then all of a sudden, you start to see people build this. This is a robot at Stanford that is climbing up walls by using this weak force that could hardly be detected. So you see the transition of technology. The community calls it exotic and weak, and then it calls it dangerous. And now we could use it at the nanoscale level. All of a sudden, you will stop climbing up the walls with this thing. Okay. All of a sudden, somebody made a thing called gecko glue. These are astronauts inside of the Vomit Comet, as they call it, testing how this can be used. And finally, I'm going to close with this picture. This is what you use graduate students for, right? This is Stanford University, graduate student climbing up is the side of the building. This is better than Tom Cruise in Mission Impossible, because that one had batteries. This one has got the uncertainty principle. You cannot turn it off. This cannot be stopped. So I hope that this interested you, and the rest of it is, of course, at dinner. Thank you so much for your attention.
Thank you.